Welcome to I Told You So, My P is Smaller Than Yours, the next chapter in the online extravaganza of Biology 417 for spring 2020.
Good morning. Today we're starting what really effectively becomes the final topic in the class, which is looking at the effect of more than one independent variable on one dependent variable. We'll start with two-way analysis of variance, and then we'll do multiple regression. You'll be covering that in lab this week. And this is Princess Sena, by the way. This is Phaedrus's mother. Remember Phaedrus from the other video? Phaedrus was one of 6 puppies that Sena had about 2 weeks after we adopted her, thinking that she had just had puppies, which turned out to be wrong. She was just about to have puppies. Anyway, this is the princess asleep on the bed. So we'll do two-way ANOVA first and then do multiple regression. And then we'll try to get to analysis of covariance. You'll do analysis of covariance in lab as well. It requires kind of a change in terminology and a change in sort of the structure of the way we'll be looking at how effects are measured and things like that. So hopefully it's not too confusing, but we'll see how it goes.
So to start motivating this idea, we'll start where we've started a lot of times. Let's just think of a hypothetical data set. Let's say we have one variable. We're going to call this variable the form of nitrogen in which we're growing some plants. So we have NH3, NH4, NO3, and NO2. These are just 4 different kinds of nitrogen that we're applying to the plant. The response variable that we're following is growth, which will be measured as milligrams per day or something like that in these plants. This would be a one-way analysis of variance. There's only one independent variable. It's the form of nitrogen that you're using, and this variable has 4 levels to it, the 4 types of nitrogen that are being used here. And you could see in this situation that it certainly looks like there's a significant effect of the form of nitrogen on growth, and you would end up concluding that the null hypothesis is false, that nitrogen does have a significant effect on growth. Of course, these might have been our experimental results as well. We might have seen what looks like here, where it looks like there's not a significant effect on growth, that it really doesn't matter what kind of nitrogen that you apply to these plants, their growth is about the same in all 4 of these treatments. And again, this is just one independent variable, the form of nitrogen. But let's say you're interested in another independent variable and the effect that it might have on growth. Let's say the variable of temperature measured in degrees Celsius. And let's say you set up another experiment where you set up some plants at 8 degrees Celsius and some other plants at 27 degrees Celsius. You have a greenhouse or something like that you're growing in. And you look at growth, and certainly it looks like there's a very significant effect of growth here. These plants they obviously really like low temperatures. They're growing much better at 8 degrees C than they are at 27 degrees C. So you end up concluding that the null hypothesis is false here as well, that there is a significant effect of temperature on growth. But an issue immediately arises based on the first discussion that we just had. What form of nitrogen did you do this temperature experiment with? In other words, for these plants in this experiment, what form of nitrogen did you feed them? Which of those 4 forms? And then likewise, if you go back to the previous 2 studies, those experiments must have been done at a certain temperature. We didn't even talk about temperature. Did you do those experiments at 8 degrees C, or did you do those experiments at 27 degrees C, or at a different, even a different temperature, a third different temperature? And so you can see that if you have an effect on, if you have an interest in the effect of temperature and nitrogen form on growth, you can't really do these things separately. You want to try to do them together and assess their effects together. So one potential solution that you could do here would be to set up replicate individuals at each nitrogen level. So think about, you have these 4 different nitrogen levels, right? 4 different forms of nitrogen. Set up a set of replicate individuals, let's say an N of 5 for each case, at each temperature. So here you have 2 different temperatures, 8 degrees C and 27 degrees C. And so now you specifically are setting up these replicate groups of individuals explicitly now at each of the forms of nitrogen and at each of the temperatures. And then you're going to measure growth. So one way to think about this, right, is you have 8 groups. there's 8 groups that are reflected here. And let's say you have an N of 5 for each one of those groups. That means the big N would be 40. And let's say you proceed through with this experiment and you measure growth in all of these different individuals. So you could get a graph that looks like this, for example. So along the x-axis, you notice that we have now some variable called nitrogen form / temperature. In other words, it's the combination of nitrogen form and temperature. And you can see that we have each combination present. Here's NH3 at 8 degrees and NH3 at 27 degrees, and then NH4 at 8 degrees and NH4 at 27 degrees, and so on across the board. And what you have plotted here is the mean plus or minus the standard error growth of the 5 individuals in each one of these 8 different treatments. And so you could think of this as a one-way analysis of variance with 8 groups. And what that would mean is that the groups degrees of freedom, right, is going to be equal to the number of groups minus 1, k minus 1, so that's 7. And then the error degrees of freedom, right, is going to be big N minus k. Big N is 40 in this case. We have 5 individuals in each of 8 groups, and we have k equals 8 groups, so the error degrees of freedom here would be 32. So you could think of it as a one-way ANOVA with 7 degrees of freedom for the group effect and 32 degrees of freedom for the error term, and these are the results that you get. But there's still a problem here. I mean, what do you conclude? Yes, maybe this group here had the best growth and this group here had the least growth, but can you say something about nitrogen, the effect of nitrogen on growth, and can you say something about the effect of temperature on growth? Are both of those effects significant or not? Are they each significant when controlling for the effect of the other, right? Is the effect of nitrogen consistent across all temperatures? Is the effect of temperature consistent across all levels of nitrogen? Are the effects of one of those variables the same across all levels of the other variable? So, you know, it's hard to discern that from this graph. I think you would agree that in looking at this graph, it's very difficult to assess the effect of temperature and nitrogen separately in this situation. So one way to resolve this is to do this as a bivariate plot, what you call a bivariate plot. Now what we have is nitrogen, say, on the x-axis, and we represent the other independent variable, temperature, as 2 different series, right? In each pair of bars, the blue bars represent the 8 degrees treatment and the red bars represent the 27 degree treatment. You can now recognize that in one sense now you don't really have 8 groups here, right? What you have are, you have 4 sets of 2 or 2 sets of 4, depending upon how you want to emphasize that. You have 4 sets of 2 temperature treatments, and each one of those sets is reflected by the nitrogen variable. Or you could say that you have 2 temperature treatments that are set up with 4 groups within them, which is the nitrogen level. So here are the 8 degree temperature groups, and here's the 27 degree temperature groups. So really what you have is 2 groups of 4 or 4 groups of 2. And thinking of it that way and plotting it as a bivariate plot really helps to emphasize that you have 2 independent variables here. So to come back to our little table that we set up before in terms of thinking about how to think about adding the effect of another independent variable into an analysis of variance, you don't have k equals 8 groups. What you have are 2 groups times 4 groups, or 4 groups times 2 groups. And if we want to use the wording from the contingency tables, we could say that temperature, say, is the row variable. Remember this terminology from the contingency table analysis. And then the form of nitrogen, nitrogen would be the column variable. And so what you have is a row variable, temperature, that has 2 levels, and you have nitrogen, which is a column variable, and it has 4 levels. So what we have are the number of rows times the number of columns, 8 treatment combinations, each with 5 replicates in them. So big N is equal to the number of rows times the number of columns times the number of individuals in each one is still 40. It's the same mathematics, it's just we're changing our language here a little bit to talk about row variables and column variables. This kind of design is called a 2x4 fully cross factorial design, and we're going to analyze it using two-way ANOVA instead of one-way ANOVA. So what we're doing is shifting from a one-way analysis of variance to a two-way analysis of variance. In making the shift, here's where we need to introduce this new language that your text introduces. This is chapter 18. And we're going to change the way we think about these models, analysis of variance and linear regression models. And the thing to recognize to start off with is that a one-way ANOVA, this slide is showing a one-way ANOVA example. Remember, you saw this slide way back in the ANOVA chapter lecture. That we can express the design of a one-way analysis of variance using that language that we had for a linear regression. Remember that the linear regression model was framed as y equals alpha plus beta x. Y is our response variable, x is our independent variable, alpha was that parametric intercept value, and beta then is the parametric slope for the relationship between y and x. So in linear regression, right, the null hypothesis was that beta equals 0, that there is no significant relationship between y and x, that x does not explain a significant amount of variation in y. Well, you can actually use exactly the same language even for an analysis of variance design. Okay, so in our example, let's say that we just had 3 levels of nitrogen that we were looking at, and we wanted to know if the 3 levels of nitrogen affected growth. We could write a model like this: growth equals alpha plus beta nitrogen form, where nitrogen form is the independent variable and growth is our response variable. In a situation like this one here, right, growth was not 0, right? The plants grew, and so the mean value for all 3 of our groups, the 3 groups are represented by the different colors, right? Green, blue, and red, and the black line is the grand mean. The grand mean for the growth of all of the individuals isn't 0. They did grow, and so the intercept is not equal to 0. It turns out this is not a very interesting result. Of course, the plants grew over time. What our real interest in is in the effect of beta, the effect of nitrogen. In this situation, all 3 of the groups are right next to each other, right? There isn't an effect of the independent variable here. The mean group of the blue, green, and red groups, mean growth of the blue, green, and red groups is all the same. Here what we would say is beta equals 0. In other words, nitrogen is not having any effect. And the null hypothesis that beta equals 0, right? We could frame this null hypothesis as beta equals 0, even for a one-way analysis of variance, appears to hold, right? We fail to reject it in this situation where the mean growth appears to be all the same in the 3 different groups. Down here, overall growth, right? The mean growth is still right here. The growth is not 0. The growth is not back here. So in this result, we are going to say that alpha is not equal to 0 either, but we're not really interested in that test either. That's not really of interest. What we're interested in is the effect of nitrogen. This beta, is beta significantly different from 0 or not? The null hypothesis in the one-way ANOVA is that all means are equal, right? Well, another way of saying that is that this value of this coefficient here, beta, is effectively equal to 0, that the growth of the plant is not affected by nitrogen form. So in this example, you could say the null hypothesis is that beta equals 0. Clearly, though, there are big differences in mean growth based on the form of nitrogen. These means are very widely separate from each other. There is very obviously an effect of nitrogen on growth, so you would end up rejecting the null hypothesis here. Okay, so in chapter 18, what we're asking you to consider is that you now start thinking about analysis of variance and linear regression as what are called linear models, and that you can use this form of expression for each one of those models. So I realize this next slide looks really supremely ugly, but actually it's not too bad. We'll work through it, and I think you'll see where this language is going, and it'll help keep you in line with the textbook when you're reading chapter 18. When we switch to a two-way analysis of variance, right, where we are introducing the effect of another independent variable, a second independent variable, we change that formula from the previous slide. And now what we're going to say is y is equal to alpha, which is, if you will, the intercept, but again, we're not really interested in that, plus the effect of independent variable 1, which we're going to reflect in beta 1, plus the potential effect of independent variable 2, which we're going to reflect in beta 2. And then what's weird in a two-way analysis of variance is you actually introduce another effect, which is the interaction between the two independent variables. This interaction may be significant and is reflected by this coefficient beta 3. So x1 by 2 equals the potential interaction between the two independent variables in their effect on the response variable. And as we go through this and the lab, I think you'll begin to pick up what this interaction term is referring to. So when you add another independent variable, you actually add two more effects, not just one more effect to that formula. You add the effect of the second independent variable, certainly, but you potentially add the effect of the interaction between them as well. So in looking at this model statement here, we can then pull out some null hypotheses that we're going to test, right? One of them could be, the null hypothesis could be that alpha is equal to 0. Essentially, this becomes just plain silly. We're going to assume that our mean variable is not equal to 0. We're going to assume that the overall mean value to our variable is not 0. That isn't really what we're interested in, and it's generally in lots of designs just kind of silly. It's not necessarily silly, but in general it is. The test of this null hypothesis is what's coming out in that intercept line that I've been telling you over and over again to ignore when you get a type 3 ANOVA table from R. This is the intercept line, and it's testing this null hypothesis, and we don't want to focus on that. And again, I'm not quite sure how to produce the table without printing that line, but this here is generally not something that you're going to deal with. You don't have to worry about this. The next three null hypotheses, though, are of interest. It's these null hypotheses that we're testing on these tables. The first null hypothesis would be that beta 1 equals 0, right? This beta 1 here is equal to 0. What that says biologically, and this is how you should be framing your null hypotheses when I ask you to frame them, this null hypothesis then says nitrogen form has no effect on growth. So that's one of the null hypotheses, that the main effect of nitrogen has no effect on growth. And the degrees of freedom associated with that test are going to be the number of nitrogen levels minus 1. So in our study that we have going in the examples so far from the beginning of the lecture, the degrees of freedom here would be 3, right? There's 4 groups of nitrogen, and there would be 3 degrees of freedom associated with that then. The next null hypothesis is that beta 2 equals 0. So this is beta 2 up here, right? And this null hypothesis framed biologically, if you expressed it biologically, would be that your second independent variable has no significant effect on the response variable. And so biologically, the null hypothesis would be that temperature has no effect on growth, and the degrees of freedom associated with that would be the number of temperature levels that you have minus 1. And in the example that we have from earlier in the lecture, there were 2 different temperatures, right? 8 and 27 degrees. So there would be 1 degree of freedom for the temperature effect here. The third null hypothesis that's going to be tested, though, is that beta 3 equals 0. And beta 3 is this one that describes the effect of the interaction between nitrogen and temperature. And this null hypothesis says that there's no significant interaction between the two of them. So the wording of interaction null hypotheses gets a little bit weird. The null hypothesis here for the interaction is that there is no significant interaction between nitrogen and temperature in their effects on growth. In other words, if there are any effects of nitrogen and temperature, they each affect growth the same way independently of the other one. Another way of phrasing it would be to say that any effect of nitrogen on growth is the same across all levels of temperature and vice versa, right? That any effect of temperature is the same across all levels of nitrogen. The degrees of freedom associated with the interaction term is simply the number of degrees of freedom associated with the first main effect times the number of degrees of freedom associated with the second main effect. So the degrees of freedom would be the number of nitrogen levels minus 1 times the number of temperature levels minus 1, which in this case would just be 3 times 1, which is equal to 3, right? So the degrees of freedom on the interaction term are things that you have to account for. There's an interesting thing, of course, that maybe you notice. Remember when I had you think about this two-way ANOVA as a one-way ANOVA with 8 groups, where the nitrogen and temperatures were all combined together in the one graph with the purple bars and everything? There were 8 groups, right? So there would have been 7 degrees of freedom in that one-way ANOVA. Well, when you break these apart into their separate effects, you notice that you do have 3 plus 1 plus 3 degrees of freedom. You have a total of 7 degrees of freedom for these 3 tests. So hopefully you sort of have an intellectual satisfaction that that ties back to those other slides, right? So it's just like the 7 degrees of freedom we had when we thought of it as a one-way ANOVA with 8 groups. But what we're doing is we're taking that one test and breaking it into 3 separate tests and dividing their degrees of freedom, which remember are additive, breaking their degrees of freedom up accordingly. So I think one way to sort of really burrow down on the application of this notation and this wording, the changes in wording, is to actually show you some hypothetical data sets and then the associated analysis of variance table that you might see in R, and really just kind of get down to the nitty-gritty and nuts and bolts so you can really see what's happening here. So the next several slides here through the end of the lecture just show you a hypothetical data set, and then the table that you would get from R when you run a two-way analysis of variance on those data. And what you're doing in lab this week is learning how to do the two-way analysis of variance in R. So first example, here's our result from our experiment. We have 4 levels of nitrogen. We have 2 different temperatures, right? So it's the same design throughout. We have temperatures of 8 and 27 degrees C, and then we have these 4 different forms of nitrogen, and we're growing, and we have an N of 5 in each group, right? And so the big N is equal to 40, and that's the same for all of these slides that we'll be going through. If you look at the graph first, if you just look at the graph, if you look at the effect of nitrogen, the mean level for NH3, the mean growth for NH3 is right about, it's right about here. The mean growth for NH4 is right about, maybe a little bit lower, maybe it's there. The mean growth for NO3 is right in here somewhere. It's the average between the red and blue bars within each pair. And the average group for NO2 is, it's right about there. There's hardly any difference in mean growth across the different nitrogen treatments. And when you look at the ANOVA table, you will find that the effect of nitrogen, which has 3 degrees of freedom, will have an F value that yields a P value that's greater than 0.05, and there's not a significant effect of nitrogen. Remember that you are missing the MS column, which you would have to add yourself, and then I put in a total column, a total row, but you have to add that yourself, right? Remember that. That's just like from the previous lab. On the other hand, if you look at the effect of temperature, the average growth at 8 degrees C is the average of the blue bars, and that's, where is that? That's like right along here, right? That's the average of the blue bars. The average of the red bars is like way down here. They're not growing nearly as well at 27 degrees C. And you notice that there is now a significant effect of temperature in the table. So here's the line showing the effective temperature, 1 degree of freedom, and this p-value would be much less than 0.05. There's a very strong effective temperature here. To evaluate the interaction is a little tricky. One of the ways you can do it is to just join the means of adjacent groups in each variable. So here's the low temperature means joined together. Here's the high temperature means joined together. And then to look at each one of these line segments and ask, are they parallel to each other, right? Is this line here parallel to this line here? Is this line here parallel to this line here, statistically speaking? Is this line here parallel to this line here? When you look at it that way, what you notice is that the effect of temperature is about the same at each level of nitrogen. And so there's no significant effect of an interaction term here. And so here's how R shows you the interaction term. Nitrogen : temp, right? So what it has is x1 and then a colon x2. This is the interaction effect in the way that R writes out these two ANOVA tables, and you see that it's not significant, right? The lines are parallel across the graph. The effect of one of the temperatures, the effect of one of the independent variables is the same at each level of the other independent variables. So in this example, the difference in growth due to temperature is about the same within each nitrogen type. Okay, so there's no significant interaction effect. Let's look at another slide. Here's another potential result that you might have seen, right, that you might have picked up. If we look at the effective nitrogen levels, so the mean for NO3 is about here, the mean of NO4 is about here, the mean of NO3 is about here. Sorry, this is NH3. So NH3, NH4, NO3, those means are all the same, but you go to NO2 and this mean is quite a bit higher. And remember, only one mean has to be significantly different for you to get a significant effect. So the effect of nitrogen in this table with 3 degrees of freedom is significant. The P is less than 0.05. But if you look at the temperatures again, if we do that same exercise for the temperatures, where's the average for the blue bars? Well, the average for the blue bars is probably right about here. In other words, these 3 blue bars are down here, and then this one is up here. The average of those 3, I don't know, maybe right in there someplace. I could even be clever and draw it with the appropriate color. So there's the mean for the blue bars. But the mean for the red bars, here's the mean for that temperature in that nitrogen. Here's the mean for 27 degrees in that nitrogen, mean for 27 degrees in that nitrogen, and then this mean is up here. Well, that's like almost, that's almost exactly the same. If we have the mean for the blue bars there and the mean for the red bars is like, it's going to be basically at the same place. So the effect of temperature with 1 degree of freedom is not significant. Then if you do that trick that I mentioned before of connecting the line segments, you notice that when you connect the blue bars like this, the red bars follow pretty closely. There's really not a big change in slope from segment to segment to segment. The effect of nitrogen is the same at every level of temperature, and the effect of temperature is the same at every level of nitrogen. So the nitrogen by temperature interaction, which has 3 degrees of freedom, is not significant in this graph. So we're just going to keep going through some examples of this. Okay, so here's another hypothetical data set. The means for the nitrogen groups are pretty different, right? So the means for the different nitrogen groups are here, 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 and here. That's a pretty big stepwise change in means. And so we have our effective nitrogen with 3 degrees of freedom, and it's statistically significant. You would reject the null hypothesis that nitrogen has no effect on growth. However, look at the temperature bars. The temperatures are the same in each one of these nitrogen groups, right? There's no effect of temperature. In NH3, they grew the same. In NH4, they grew the same. In NO3, they grew the same. In NO2, they grew the same. So there's no significant effect due to the temperature effect, which has 1 degree of freedom. And then looking at the interaction effect, the slopes of these line segments are all pretty much the same as you look at the different independent levels. These, in each segment, these lines are pretty parallel to each other. In other words, there is no difference in the effect of nitrogen on growth at different temperatures. And so the interaction effect with 3 degrees of freedom is not significant. Okay, this gets a little bit more interesting when you look at these graphs. If you look at the effect of nitrogen, so just go across the nitrogen groups, right, and look at what the mean value is for the different nitrogen groups. The mean for NH3 is the mean between these two bars, and that's about here. The mean for NH4 is the difference in means here, so that's probably about here. The mean for NO3 is about here, and the mean for NO2 is about here. There's big step changes in growth depending on the form of nitrogen that you have, and so you end up concluding with 3 degrees of freedom that there's a significant effect of nitrogen. But now we can look at the effect of temperature. You notice that the blue bars for temperature are all very systematically below the red bars for temperature. So the average growth for 8 degrees C is the average of the 4 blue bars, and the average of the 4 blue bars is, you know what, it's probably right about here, something like that. But the average for the 4 red bars, is like way up here someplace. That's a big difference between the red and the blue bars. So in this case, there is a significant effect of temperature on growth. But when you look at these lines right here, compare the red line to the blue line, that segment, compare this red line to this blue line in that segment, and compare this red line to this blue line in that segment, these slopes are all about the same. They're pretty parallel to each other. And so the nitrogen by temperature interaction, which has 3 degrees of freedom, is not significant in this graph. The effective temperature is the same in each nitrogen form, and the effective nitrogen form is the same at each of the 2 temperatures. Okay, so therefore there is no significant interaction between nitrogen and temperature. So on this table, you would reject the null hypothesis that nitrogen has no effect on growth. You would reject the null hypothesis that temperature has no effect on growth, but you would fail to reject the null hypothesis that there is no interaction between the effect of nitrogen and the effect of temperature. There does not appear to be a significant interaction there. Okay, so now for these slides, now we get into some weird effects, and it becomes a little bit complicated to talk about because the interaction becomes significant. If you look at the effect of nitrogen, right, you can compare the means of the different nitrogen groups, right? So you have 4 nitrogen groups. The mean for NH3 is here. The mean for NH4 is here, averaging across the 2 temperatures. But the mean for NO3, right, the average between the mean at 8 degrees and the mean at 27 degrees, that's like up here somewhere. And the average growth in the NO2 treatment is maybe a little bit lower, maybe right here, but these 2 means are pretty different from these 2 means. So nitrogen with 3 degrees of freedom has a significant effect, and you're tempted to reject the null hypothesis that nitrogen has no effect on growth. If you look at the effect of temperature, right, in the first 2 nitrogen groups, NH3 and NH4, there's clearly no effect of temperature, right? The plants grew the same at each temperature, but in the NO3 group, the plants at 27 degrees grew much better, and in the NO2 group, the plants at 27 degrees grew much better. The result of this is that the average for the low temperature treatments is probably right about here. It's the average of those 4 blue bars, but the average for the 27 degree treatment is the average of the 4 red bars, and the average of the 4 red bars is probably up here somewhere. So we have now a significant effect of temperature, right? The P is less than 0.05, and you reject the null hypothesis that temperature has no effect on growth. Here's where it gets complicated. If you draw line segments joining the blue means like this, and then you draw line segments joining the red means, you notice that in this segment, right? So in this segment, the red and blue lines are basically parallel. In this segment, the red and blue lines are essentially parallel. But in this segment here, these lines are not parallel. The red line jumps up very sharply and the blue line stays relatively flat. These lines aren't parallel to each other. Another way of saying this, you've rejected the null hypothesis that temperature has no effect, and you've rejected the null hypothesis that nitrogen has no effect. But the effect of temperature depends very strongly on what kind of nitrogen the plant is given. In NH3 and NH4 treatments, there's no effect of temperature, but in NO3 and NO2 treatments, there's a very strong effect of temperature, right? So the effect of temperature varies depending upon what nitrogen group you're in. That means that the nitrogen by temperature interaction is significant. It has 3 degrees of freedom, and it would have a very small p-value. You'd end up rejecting the null hypothesis. As a point of departure, as a little side note, when you reject the interaction effect in a two-way analysis of variance, it actually makes it kind of difficult to interpret the main effects. You can't really conclude that temperature has an effect on growth because temperature only has an effect on growth in certain nitrogen groups, right? Likewise, you can't really say that nitrogen has a significant effect on growth because whether or not nitrogen has a significant effect on growth depends on what temperature the plants are being grown. So making conclusions regarding the main effects becomes a little problematic if the interaction term is significant. In this situation, you still have something similar. Even though these two blue bars are somewhat higher than they were on the previous slide, you still have the same problem going on. If you look at the effect of nitrogen, NH3 mean is there, NH4 mean, the NO3 mean, the NO2 mean, there is a significant effect of nitrogen on growth. If you look at temperature, the average blue bar, the values of the blue bars is probably right about here. The average for the red bars, though, is a bit higher. It's up here. And so there is a significant temperature effect in this situation. And if you join the line segments, you notice that the effective temperature changes depending upon what nitrogen group you're in. So we could join these two blue groups here and these two red bars here, and those lines are pretty much parallel to each other. But if we join this red bar to that red bar here and then join the blue group here, you notice these slopes are fairly different. In other words, the differences between the temperatures is not staying the same magnitude. And then here, again, these line segments are roughly parallel. But the problem arises here, these line segments are not parallel to each other, and that results in a significant interaction effect. The effect of temperature on growth depends upon what form of nitrogen you're looking at. At NH3 and NH4, there is no effective temperature, but in NO3 and in NO2, there is an effective temperature. Again, same thing. We have here a significant nitrogen effect, right? The means for the different nitrogen groups are different. We have a significant temperature effect. The mean of the blue bars is pretty significantly different from the mean of the red bars, but there's a very strong interaction effect here in that the slopes of these lines across these segments for the red and the blue lines joining the different levels of temperature, these slopes are very different from each other, and so you have a significant interaction effect here as well. And then finally, in this hypothetical result, we see something, you don't see this very often, but this can happen sometimes. Let's take a look at the effect of nitrogen form. So look at the means for the different nitrogen groups. The mean for the NH3 group is the difference, is the average between that mean and this mean, and that average is, it's right about here or something like that. The average for the NH4 group, that's about here. The average for the NO3 group, lo and behold, that's right about here. And the average for the NO2 group is right about here. Those four means are right on top of each other, and what you find is that you fail to reject the null hypothesis. There is no significant effect of nitrogen on growth. So let's look at the different temperatures, right? The average for the blue bars, the average of the 4 blue bars is what's kind of right in the middle. It's right about here. That's the average of the 4 blue bars. The average of the 4 red bars, the 27-degree treatments, the average for the 27-degree treatments is right about there as well, and you end up concluding that there is no significant effect of temperature either. This is very disconcerting, right? It's very unsettling because there's all kinds of differences among these bars, and yet neither one of your treatments has a significant effect on growth. If you join the blue bars to look for interaction and then join these other bars like this, you notice that these are about as anti-parallel as they can possibly be, right? They form a big X right in the middle of the graph. There's a very strong interaction effect. There's a very significant interaction effect happening here, but there's no main effects. So even though, for example, plants at 8 degrees grow really fast compared to plants at 27 degrees, when you give them NH3, there's still no main effect of nitrogen, and there's no main effect of temperature. This is kind of a nightmare data set that you can get, and sometimes you can have this happen where there are no main effects to be seen, right? There's no main effects. The p-values are both a lot greater than 0.05 for your 2 main effects, the effects of your independent variables, but there's very strong interaction effect. The last thing to make sure that I note before we leave this is make sure that you're looking at these degrees of freedom and how they're all adding up, right? The total degrees of freedom is still always going to be big N minus 1, even in a two-way analysis of variance. So remember, there were 5 individuals in each of 8 groups, so that's 40 individuals in total. So the total degrees of freedom is 39. The degrees of freedom on the nitrogen effect, there's 4 levels of nitrogen, so there are 3 degrees of freedom on the nitrogen effect. There are 2 temperatures, so there's 1 degree of freedom on the temperature effect. The interaction effect always has the number of degrees of freedom on each independent variable multiplied together. So 3 times 1 is 3. So there's 3 degrees of freedom on the interaction effect. But when you report these results, right, you need to report an F ratio with a certain number of degrees of freedom to it. And the first number of degrees of freedom is for the main effect you're testing, but the second number is always for the error term, right? What R calls the residuals and what I want you to label as error. These degrees of freedom here all have to add to 39, right? So the degrees of freedom on the error term for a one-way analysis of variance, right? Remember, in a one-way analysis of variance, the error degrees of freedom were simply equal to big N minus K. Well, we don't really have K anymore in a two-way analysis of variance, right? Because we have these different effects we have to account for. So I think the easiest way to take care of the degrees of freedom on the error term is you simply take the degrees of freedom for your main effects and your interaction effect, which in this case is 3, 1, and 3, or 7, and just subtract that from the total degrees of freedom, which is 39, and that gives you the error degrees of freedom at 32. So if you were to report, say, the effect of nitrogen in this situation, you would say that it has an F ratio with 3 and 32 degrees of freedom equals some value. I don't have any values written here, right? P greater than 0.05 or whatever the p-value is that comes from R. But just keep track of where those error degrees of freedom come from as you're going through these two-way analyses of variance.